Hello, shall we start?
Yes, sir. Yes. Please start.
Good evening to all of you. So today we were supposed to discuss some sessions, some problems related to the sessions that we already have completed. But since there are two topics that have been actually asked by two of the participants, like one is in graph theory, the other one is Laplace transforms. And I will try to give a brief overview into these two topics, starting with graph theory first. So graph theory module in SageMath is actually a very extensive module, and therefore it gives a lot of options for doing several things in graph theory. So graph theory, it's a branch of discrete mathematics, and therefore there is a lot of scope for computation as well. Unlike in the case of continuous mathematics, discrete mathematics is much more suitable for what you call this computational software. So let us start doing certain things in graph theory, trying to define graphs, trying to do some operations on these graphs, etc., etc. Let us see that what are the options available in graph theory. As I already told, the graph theory module in SageMath is really extensive, and maybe one complete textbook can be devoted for understanding graph theory in Sage Mathematics. Therefore, and you need not have to understand all these things. If you are interested in doing graph theory using SageMath, maybe you can have a look at that and take only those commands that are actually required by you. So it's not necessary to understand everything in Sage Mathematics for doing this graph theory. Let me start sharing the screen. So let me just share the link of the document file where I will be copying and pasting first. Okay, so the very first thing that we need to draw a graph is that, see, the very first thing that we have to understand is that in graph theory there are two things that we need to actually do. One is to define graphs, understand certain properties of graphs, and that's one thing. Second is to see the result of our actions in a visualized form, right? In a visualized form. So we need to see how exactly the graph looks like. So the very first thing is to define a graph, and after that define something extra or modify that graph, and after that finally see the graph, just as in the case of plot. Here we don't have to use the plot command, but instead of that, of course plot command also can be used, but for constructing a graph we need to use a built-in function called graph. So let us define a graph G first of all. So G is equal to graph. So open close bracket is there. After that, what we are going to do is we are going to define the connection between vertices and vertices. That's what the edges is. If there are no connections at all, we can actually define a graph with all isolated vertices. Let us see how to define a graph with all isolated vertices first. So let us do it like this in curly braces: 0, 1, 2. Graph with 3 vertices, nothing else. Maybe we can ask what this G is. Oh, sorry, we need, even if it's empty, we need to define it like this problem. No connection. Sorry. Okay, maybe I will just define a graph which is not empty. Let me define a graph which is not empty, because after that we'll try to convert this into 1 to 2, maybe 2 to 0. If I define like this, let us see. G is equal to graph. 1 I have defined from curly brace 1, and after that 2. Okay, just see what is the issue here. Graph G is equal to graph 0. Okay, let me just modify it slightly.
So you have written semicolon.
Am I using semicolon?
You have written actually.
Yes.
Here this is not semicolon, right?
No, sir. Previous graph.
Oh, previously I was using semicolon there. Oh, sorry. Then, okay, 2 to 1. So now we have defined a graph with 3 vertices. 1 is one vertex, 0 is another vertex, and 2 is the third vertex. So we have vertices 0, 1 and 2, and it says a graph on 3 vertices, but we don't know how exactly this looks like. Let us show the graph as well. So the graph is here. So the connections are defined here. 1 to 0 is connected, and 2 to 1 it's connected. Now we can further modify this, keeping on adding 3 colon to 4, say, and 4 and 2, 3 to 4 and 3 to 2. Let me define 3 to 1 as well. So I can do it like this. So the structure is this. I need to define from which vertex to which vertices. Okay. The way in which we define this vertices to vertices connection is known as a dictionary. Okay. So in curly brace, when we write one element colon a list of elements, we call this structure to be a dictionary in Sage as well as Python. So in the dictionary, what we have to define is, this is something known as the key of the dictionary. The key of the dictionary is the originating point, from which vertex the connections are originating. Therefore, we say that the vertex is 1, and to vertex 0 there is a connection. From vertex 2 there is a connection to 1. From vertex 3 there is a connection to 4, 2 and 1. So we have altogether 0 to 4, 5 vertices. So if we ask for 5 vertex graph, the connections are here. So we are getting it like this. So this is how we define graphs, and we add edges. Let me update the Google document. I have already shared the link to that. So this is the very simple way of defining a graph. Now, in fact, we can, just as in the case of plot, we can add graphs as well. So just use the plus symbol. Suppose that we define G to be this, and suppose we define slightly modifying H to be just, so graph thing is really necessary. So H to be this, so 1 to 3. So remember that here there is actually a kind of confusion that we have actually 2 graphs and we are defining the same kind of vertices, same number of vertices here. So show H plus G. See here, what happened is, even though we have labeled the vertices in G to be 0, 1, 2, 3, 4, and vertices in H to be 1 and 3, because there is actually confusion because we are using the same symbols. What Sage did is H it converted to 0, 1. Okay, in H, in the H graph it converted the vertices to 0 and 1 and connected, and in the G graph it converted the vertices from 3 to most probably in the same order. It converted the vertices with labels 3 to 6. That's what I did. That's what it did. So automatically the conversion happened. Therefore, if you are adding 2 graphs without creating any confusion, they will be properly managed by Sage. Now there is one more interesting thing is that now we can say that the vertices are not actually coming in proper order, I guess. 3 to 2, 3 to 4, 3 to 5, 3 to 6. Now if you want to arrange these vertices in some cyclic order, we can give an extra command. So let us just remove this. So setting the layout. Let us set the layout. So the setting the position, we have to set position, set layout, not layout. So we want to arrange the vertices in some circular manner. So if we do this, we can see that now the vertices are appearing in the following manner in the anti-clockwise direction: 0 to 1, 1 to 2, and 2 to 3, 3 to 4. You can see that the vertices are arranged like this. Previously, we can say that the vertices are appearing like this. Now, there are a few other options as well. If you check the documentation of this layout options, then you can find that there are several. So if you ask for setting the position, so set pose, maybe I don't know whether we will get a result. No, set pose is not graphs.set pose. No, because there are the commands that we apply that particular object using a dot. These things are usually known as methods, and getting information about methods is a little bit difficult, it seems. Okay, let me just try. So graphs. Oh, graph only, I think, not graphs. So the position we can specify actually here itself, it seems. So there are a few options like this we can specify. List of edges, bypass, auto, all these things are possible. Now instead of this, instead of using the vertex names as 0, 1, 2, 3, etc., we can change that vertex names as well. Okay. So documentation can be accessed by using this graph command. So this is how we define basically one what you call a very simple graph. Now we are going to see some extra options. So these are the simple definition kind of things. Now let us see. Now let us define something known as a complete graph. Okay, complete graph can be defined directly. G equal to. For that you have to invoke another library called graphs, small graphs. Remember that previously we used a capital GRAPH, graphs. From the graphs module, we are taking a graph of 4 vertices. Complete graph with 4 vertices. So we get this to be a complete graph. And if you want to see this, zero, 1, 2, 3. So complete graph is here. Let's use this graph itself, because complete graph there is nothing extra special to do. Suppose that we want to add an edge after defining the graph. So for adding an edge after defining the graph, what you are supposed to do is you need to just specify between which vertices you want to add the what do you call it, vertex. So edge. So 2, 1 already there is an edge. So suppose we define 2, 3. 2, 3 and see. So 2, 3 also an edge is added. So add edge, that's the command that we are supposed to use for adding a single edge. Now suppose that we use this command once again. Suppose that we add instead of suppose we want to add already there is an edge from 2 to 1. If we try to add 2 to 1, what will happen? Once again, 2 to 1 already there is an edge, please see. So if we add 2 to 1 again, nothing actually happens, because we need to clearly say that we want a multiple edge. We want to turn on multiple edge option. Then only that extra edge will be added like that. So we need to allow multiple edges. That is what we want to add, right? So we need to turn on adding g dot allow multiple if you do this, then 2 1, if you see, you can see that 2 1 is again added as a multiple edge. So we need to turn on this allow multiple edges option to be true. Similarly, we can turn on the loops also, because loops by default it won't work. Suppose that we add 2 2. So by therefore, which essentially means that by default we'll be defining a simple graph. Okay. So if you want to define loops, then again you need to turn on allow loops to be true. So if you do that, 2 2 a loop is added. So the model is that we need to explicitly permit the addition of multiple edges as well as loops. Otherwise, it won't work. Now, in fact, at the time of definition of the graph itself, we can do all these things. We can keep on we can add, we can give these options like define G to be something, and after that, in the beginning itself, we can do all these things like this. We can in the beginning itself say that multi edges equal to true, loops equal to true. After that, define 1 to 0, 1 to 1, 2 to 1 1, say. A positional argument follows. Maybe this I need to put it towards the end. Yeah. So here see that 1 to 0 is already there. 1 to 0 is okay. Where is 1 to 0? Okay, one is repeated, sorry. 1 to 0, I have to give the key once, only once. I cannot use it multiple times. 1 to 0 and 1 to 1. Okay, 1 to 0 is here and 1 to 1 is here. 1 to 2 is here, 1 to 2 is again there. 2 to 1 and 2 to 1 repeated. 3, 4, 2, 1. So we can give the option of multi-edges here itself. Therefore, we don't have to use allow multi-edges option afterwards. Allow multi-edges, allow loops. So this is required if you are defining the graph. This is the definition of the graph. If you are not giving the options like multi-edges and the other things, then you may not, you will not be allowed to add parallel edges. Multi-edges means parallel edges and loops. The graph will be a simple graph by the original definition, if you do not permit that explicitly. Now one more important thing that we need to remember is here, okay, I am just making use of this graph again and again, but let me remove this 1 to 0, not necessarily now, removing these options and show G. I am getting a graph like this. Now suppose that I want to create a copy of this graph, H equal to G. Okay, so what is G plus H therefore? G plus H, we can see that it's nothing but this much. Now, one small thing that we have to remember here, that here we have connection from 1 to 0, 2 to 1, 3 to 4 to 1. Okay, we have taken H to, we have taken a, we actually what I wanted is to save a copy of G into H so that I can do something on H, and G will be remaining as it is. Okay, so G will be remaining as it is. Okay, so now suppose I add 1 to 4. So see that the edge 1 to 4 is not present in G, therefore 1 to 4 must be present in only H. So if I add G plus H, if I find G plus H, it must contain 1 to 4 only in H. But see what's happening here. These two graphs become exactly the same. So even though we have taken a copy of G inside H, what happens is if you are adding an edge to H, it affects G as well. Therefore, by the symbol H equal to G, we have not actually made a copy of G, but instead we have made a reference to G. So H is containing exactly the same graph as that of G. Whatever you do on H, it's going to affect G as well. Whatever you do on H. So this is not actually the method to make a copy of H. Okay, make a copy of G. So to make a copy of G, what you need to do is you need to explicitly make use the copy command. So here the issue is that if you do this, maybe we can do one more thing. Suppose we add G 2, 4. That's also getting affected. Operations on H. Okay, so if you want to do something which affects only one of them, then you need to make a copy of that. So copy. The copy command we need to use. Now let us see. One graph must have 1 to 4. The two graphs must be different slightly. Okay, to understand this properly, maybe since we have added two edges, it's better to just suppress one of them. We can see that to H there is an extra edge. So how many edges are here? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. This is correct. 1, 2, 3, 4, 5. Yes, that's correct. So without getting G affected, if you want to do some operations on H at the same time, making a copy of G into H, you need to use the copy command. Otherwise, both these things will get affected. Now we can create an empty graph as well. If you just use G is equal to graph, you will get an empty graph, and you can of course add. Okay, show G. So now output, because it's empty, some plain region is appearing. Now suppose that we add G to be, we take G to be equal to this, and suppose we add vertices. Add vertex, say 1. There is only one vertex, or 0. You can even add a range of vertices. I think you should use vertices for that. 1, 2, 3. Maybe you can even add edges after that. Edges. So how do you do that? 1 to 2, 2 to 3. So you can start with an empty graph and you can keep on adding. Now we have seen that we can actually define G to be a complete graph, because the graphs module in Sage actually consists of several graphs, like a complete graph, bipartite graph, complete bipartite graph, etc. All these structures can be created. Now if you want to add a complete graph to an existing if you want to add a complete graph to an existing what you call graph, we call a complete graph inside a graph, a complete subgraph inside a graph to be a click. So we can add a click as well. Suppose we use this. So already there are vertices, we know. Now let me just add click. So for adding click, there are not many options that we need to specify. What we need to just say is on how many vertices we want to add the click. So click is of how many vertices. So say I already have 1, 2 and 3. Suppose that I add a click on 3, 4, 5 and let us see what this is. See that the existing third vertex is used, and vertices 4 and 5 are created in addition, and using these 3 vertices the connection is made. Now if I use, instead of this, suppose I use 4, 5, 6, then I would have simply got a component, a click component like this. Already the connections are made here, and after that a click is added. And we can even list the edges using this command. Already we have g.edges or print g.edges. So 1, 2, none means there is no label. We can actually specify label also, but that is an internal thing. I didn't see it appearing on the graph inside of that. Maybe I have to turn this vertices. So 1, 2, 3, 4, 5, 6. These are the edges and vertices. Just like adding a click, there is an add cycle option as well. Take G to be equal to graph. Let us define 0 to 1, 1 to 2, 3, something like this. Adding a cycle, in the order 3, 4, 5, 6, so a 4 cycle added. So 3, 4, 5, 6, there is a 4 cycle. Already there is 0 to 1 and 1 to 2, 3. 0 to 1, 1 to 2 and 3. So a cycle. Maybe we can add a path as well. Three, 4, 5, 6. A path is added already because there is a connection from 1 to 3. Those connections are protected, preserved. Now we have seen adding cycle. Now instead of, as I already told, instead of giving the names one by one, we can actually give a range as well if you want. You can just specify that create a cycle of on these vertices like this. So no, not this one. Okay, when path is also fine. Range 2 to 7. Let me see if it. So if you ask for range 2 to 7, it simply means that 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yeah, 2, 3, 4, 5, 6. Because see that the range command actually it's left close, right open interval. Range command gives left close to right open 7. Therefore 7 will not be included. So we can add a cycle like this as well using the range command. So if you do not want to specify. Now one more thing is, now we can add a label also. 1, 4, but see that label is not appearing. So for that, maybe we have to turn on the edge labels equal to true. Oh, well, then it's not coming. Or let me just go the other way. Yeah, this is the, but where is that? Yeah, the new edge. But unfortunately, the thing is that we have not defined any label for any other thing. Therefore, it's coming like this: none, none, none. Only for this one, it's appearing as new edge or 1, 4.
Well, here labeling the particular name of the vertices.
Sorry.
So here labeling meaning that particular name of the vertices.
Edges.
Edges.
Vertices are already labeled using 1, 2, 3, 4.
Suppose I want to give some A, B, C, D name
I think you should be able to do that here itself, because suppose A, maybe you have to give it in quotes, because otherwise it will be taken as a variable name. So C to B, same graph I am expecting. So say D. If I do this, I think this should work. Yes, we are getting it. So you can directly do that while defining itself. So instead of using that, if you are using the 0, 1, 2, 3, you don't have to use this what you call quotes. But if you are using a string, you have to do that. Now U1, U2, U3, etc. also you can do same way. If you want U1, U2, U3, etc., you may do that. A1, A2.
Okay.
So edge labeling only we need to turn on like this. Vertex levels are anyway appearing. That's the usual thing, right? Because in a usual graph, we always, even if we do not, even if you do not label the edges, we know that if it's a simple graph without having any loops or multiple edges, this is not necessary. Labels are not necessary. Because by using vertex name, it's if the vertices are V1 and V2, the edge is simply labeled as V1, V2. If it's not if it's a simple graph. If it's not a simple graph, then only this label is required, edge label.
Its default the weight is 1. So get that is that one, is level 1.
A default?
Wait.
Sorry, I didn't understand.
So here edge level means that weight of the edge, right? So,
See, something is appearing here. You can see that there is a 1, 4 appearing. Okay, that actually got disappeared.
okay. So
See, you can see that the edge label is here. Edge label.
Okay.
So label of the edge. That's it. It's we are naming that. We are naming that label, that edge.
That particular edge.
Yes. If you
so
want,
how to get weight of the
how to get
weight of the edge?
Weight by default the weight will be 1. But if you are using a weighted graph, you need to specifically mention that. We will come to that.
Okay.
This is not weight or anything like that. This is simply a label. That's it. Name. Nothing more than that.
Okay. Just moving the edge.
Yeah. We are naming the edge. See, as I told, this is applicable. This is required actually only if you are using multi-edges or loops. Otherwise, there is no point. I just showed that the option is here. That's it. Okay, as I told already, we have already seen how to add vertices, but if you have only a single vertex, you don't have to use add vertices. Where is that add vertices? Yes, this add vertex can alone be used if it's a single. If you want to just add, but surprisingly these things exist. I don't really understand the need of this add vertex, because add vertices itself is more than enough. So this also can be done. This one I'm saying. This option is also there. Add edge, add edges, add vertex. Sorry, here you don't have to use the list. This is just a single vertex. So this is an isolated vertex. Add vertices if you want. You have to use the add vertices command and then give the vertices in a list. So instead of adding cycle, you can define, as in the case of the previously defined complete graph. Just like that, you can add cyclic graph as well. G equal to graphs cycle graph. Say cycle graph on 5 vertices. Zero, 1, 2, 3. If you do not specify any such thing, it will be coming like this. And as in the previous case, you can see the vertices here. Zero, 1, 2, 3, 4 are the vertices. So you can get the adjacency matrix as well simply using G dot adjacency matrix. See that I have already defined the graph here. Then only you should apply this G dot adjacency matrix. Otherwise, this is not going to be useful. We just update the Google Sheet. So just as in the case of cyclic graph, so here we use cyclic graph. Similarly, we can have a path graph. So the options, all the options available can be probably seen. Path graph for 5 vertices means, so 0, 1, 2, 3, 4. So we get a path. Maybe we can, after that we can add an edge and ask if it's a cycle. G dot add edge. So 1 to 4. What happened here? Add edges. What is the previous command? Add this is the same. Why is it not giving? So G is defined to be this. Add edge 1 to 4. I think because we have defined this G to be an already existing graph. Is it because of that? I don't know. Let me just make a copy of that and see. Why is this not giving? 1 to 4 already. Vertices are 0, 1, 2, 3 and 0, 1, 2, 3, 4. Why is it not adding an edge is what I'm wondering. Okay. Edge vertices are here. That is surprising. Add edge path graph 5. So is it working for complete? No. So cyclic graph 5. Okay, here it's working on the path graph, but somehow it's not working. 1 to 4.
I think so.
Yes.
They are all maybe.
Sorry? No, that's not giving. Okay, let me just do another thing. Maybe it's a problem with that pathgraph command. Okay, let me just try to define an empty graph first. Empty graph G add path range 5. So what I did here, 0, 1, 2, 3, 4, I added 0, 1, 2, 3, 4, I added one path, and after that I added another edge 1, 4. Here it's working, but somehow this is not working. I don't know why it's like that. It's a problem with maybe in some of your machines maybe it's working, but I'm not seeing that work here. This is anyway working. It's the only thing I know. Okay, now we have the same graph, adding edges, everything done.
Sir,
Yeah.
Sir, am I audible?
Yes, please.
Sir, I think the problem that edge you have added, they are overlapping. So when I change that layout to circular, then it is showing.
So was it there? Are you saying that it was there? It was overlapping kind of thing.
There.
It was overlapping kind of thing was
Yes,
happening.
yes.
Okay, set layout.
Yes,
Set layout we used. It's coming properly, right?
Yes.
Okay, that can be the reason. Oh, it's not showing. It's there, but it's not showing. Okay, let me just try. If that's the case. Path graph 5 and added, so 1 to 4. Okay, then it's coming. Maybe it's through the same line, probably it's showing. That is not actually a correct thing. It's probably a bug that the line is getting, it's going below that. It's not actually a good thing, but it seems that it's correct. If we suppress this, it's not appearing. 1 to 4 is not appearing. But if we change the layout, it becomes visible. That's something strange, but okay, anyway, it's working. Okay, now let me just copy this. So we have the graph G here already. So now we can find, so see that for reaching from 0 to 3, there are 0 to 4, there are two paths, 0, 1, 4 and 0, 1, 2, 3. So we can list out all the paths. We can list out all the paths. All paths from 1 to 4 or 0 to 2. So the paths are 0, 1, 2, 3, 4 and 0, 1, 4. These two paths are there. And if you have created some graph and if you want to test if it has already some loops or not, of course, if we are creating our own graphs, the loops are not going to be there for sure. But suppose that while doing some problems in between, if the loops appear or not. We can check if it has loops. So see that G is this. Now we know that G has no loops. We can ask if G has loops. G has loops. Maybe we can add, let us permit loops. And add a loop. So will the cycle also work? Let us see. No. No. There is no way to test that. For that we may have to list out all the cycles and see. So of course, each cycle is possible. Is this a cycle? We can of course ask, but Haas cycle, I don't see there is an option. All paths. So what about all cycles? Suppose we have this. Will this work? And now I'm just trying. No. So G has no such options. All paths are there, but not all cycles. So is a cycle can actually be asked, just like what did we previously ask? Has loops. So let us take this to be a cycle itself. Cyclic graph on 5 vertices. So each cycle is correct. Now we can take, okay, let us just take one of the graphs that we have defined previously. So graph from here to here, 3, 4, 6 cycle added. Let us take this. We can construct subgraphs as well using the same kind of techniques. So add cycle is already here. So G is here. Let us take a subgraph with vertices. Here we have 5, 6, 4, 3. Let us take the vertices 5, 6 and 4, 3 and form a subgraph. G dot subgraph vertices 5, 6, 4, 3, which is 3, 4, 5, 6 of course. Show edge. 5, 6, 4, 3 we get as the subgraph generated by these vertices. So whatever edges are connected in that, we are getting only those vertices. So we can even get a graph with only the edges connecting some of them. So instead of taking all, we can even take which is equal to, so suppose that we take graph consisting of edges, say 5, 6 and what are the things here? 5, 6 is already here. And 0, 1, 2, 3. Okay, edge we are specifying. So 0, 1. What happened here? Show E. G is subgraph 5, 6. G dot subgraph edges. Okay, sorry, we need to specify these are the edges. Unlike the yes. Oh, what are the things that we got? So we got subgraph edges 5, 6 and 0, 1. Therefore we got all the vertices. Sorry. So what we got here is 0, 1, 2, 3. We got a graph with all the vertices but only these two edges. Okay, that's it. So subgraph edges only these two are taken, but all the vertices are taken.
So H is an induced graph actually.
Yes, H is induced. Correct.
Induced.
Correct. Induced subgraph.
Yes, sir. Induced.
G is also. Sorry, E is also. No, E is not. E is not. In the case of E, what's happening is all the every edge other than this 5, 6 and 0, 1 are removed. That's it. Is it not? This is what's happening, right?
Yes. Is it possible to remove these vertices?
Means deleting the vertices.
In graph E, these vertices 4, 5, other which are isolated.
Okay, I understand. So, remove. Okay, add edge. Okay, let us just try to see. I'm not seeing what exactly the option is. Let us just try. If this is giving the correct thing, it's fine. So let us. Already we have this much. So if we ask for removing. just we have seen. Let's try, just try and see what's happening. No, remove vertex. So I am not seeing any remove option anywhere. Remove loops is there. Remove edges is there. Therefore, I think once you define the graph to be, maybe you have to just, okay, so remove edges is certainly possible. Okay, delete is probably the keyword for that, not remove. Okay, delete vertex is what we have to do, not remove. That's the problem. Delete. So what happened here? So let us see G previously. G was, which vertex we removed? The vertex 3 we removed. Okay, 3 we removed. Therefore, connections are 4, 5, 6 and 0, 1, 2.
Yes, sir. It has to be removed.
Yes, it's removing, right? So let us see, so isolated vertex we were discussing about, but how do we find, okay, once we have the, a way to check if it's an isolated vertex I am not seeing, I am just trying, okay, let us see. So already we have defined G to be this. So previously what was that? Okay, let us just take this. This is here. So if you remove which vertex, if you remove the one vertex, the 0 will become isolated, right? One vertex, 0 will become isolated. Okay. 0 and 2 are isolated vertices. Now, degree of 0. Okay, degree of 0 we are getting to be 0. So if you want to remove all the isolated vertices, we can probably do it in a loop, because we already know that the list of vertices we can find using G dot vertices, right? So 0, 1, 2, 3, 4. If you loop through all the vertices, and then we can remove all the isolated vertices as well in loop.
Yes, sir.
Check degrees in loop and remove them one by one. Or maybe even delete vertices is also there. I don't know. Equivalent command 1 and 2 if you give. No, that's not there, it seems. Vertices, okay, 1E. Yes, that's there. Delete vertices is also there. Delete vertex is there for single, and vertices for multiple. 1, 2, 3. So to make it simple, to make a graph simple, we can remove loops as well as multiple edges. So for example, suppose that we have already defined a graph with allowing multiple edges for some reason. Suppose we allowed it. Now suppose that we add edge
0, 1.
0, 1 is already there, right? Okay, multiple edge we want 0, 1. Okay, let us see. So 0, 1, there are now 2. Now the question that if, okay, has multiple edges, I think edges or edge, I don't know exactly, let us see. Yes, has multiple edges, that's true. So remove multiple edges, ask the same question again, or maybe when we can see. So remove multiple edges can be used like this, and remove loops also can be used in the same way. And in fact, we can see all multiple edges, list all multiple edges if we want. Just use the multiple edges command. So 0, 1, 0, 1 and 0, 1. This is, so in case we provide labels, that also will be appearing here. So 0, 1, 0, 1, that's the, these are the multiple edges. Now if you want to just see the number of vertices or number of edges, of course you can take the add vertices and find length, but that's not necessary. The usual graph theory terminology that order and size, I think size corresponds to the number of vertices, size corresponds to the number of edges, and order corresponds to the number of vertices. So number of vertices is G dot order, and edges is G dot size. And we can in fact find neighbors as well. So to find out the neighbors of a vertex, just use the neighbors. And we can merge vertices. We can we have already seen adding edge, delete edge we can do, merge we can do. So all these options are there. All these usual options, and all these usual options have the usual name as well. Show the number of vertices.
Is there any option for directed graph?
Yes, yes, we are going to that. And of course, after most of the options that works with this graphs works with the directed graph. The only thing is that we are having a direction, right? So all of the commands are more or less the same. The only definition is going to be different, and of course there are certain extra properties, but most of the concepts are going to be valid even there. I will just try to explain that also, that directed graph. The last thing that I wanted to say is neighbors. Okay, G dot neighbors of a vertex. Neighbors of one. So 0, 2 and 3, these are the neighbors. So now we can remove all the neighbors in a loop and make it probably and delete the vertices as well. Delete the edges as well. Suppose that we have 0, 2, 3. Now if you remove 1, 0, 1, 2 and 1, 3, this vertex 1 will become isolated. So for that you can use delete edges, okay, to make it isolated. Okay, now digraph. So digraph, the definition is, as I already told, the definition is quite straight. Instead of graph, use digraph. Maybe we can use the symbol D. Digraph. Zero to 1, 1 to 2 and 1 to 3. Here if you add an edge, remember that that's not going to be multiple. If you are adding from 2 to 1, that's not multiple. Add edge 2 to 1. Here the direction becomes important, because previously 1 to 2 or 2 to 1 doesn't make any difference, but here 2 to 1 is different. And in addition, okay, so using the same graph again, the show G versus G previously. Okay. So to see the edge connectivity and vertex connectivity, as usual, they have the usual names. Edge connectivity, vertex connectivity. So both are 1 and 1, and maybe if we define 1, 2, 3, let's make it a little bit more bigger, 3 to 4, 5, 6, and 5 to 1, say. I'm just trying something randomly, 5 to 1. So the vertex connectivity as well as edge connectivity both are 1. So maybe we can ask if something is the cut vertex or not. So we can simply ask, is cut vertex? So we can say that 6, 4, 2, 1, 0, sorry, 6, 4, they are not cut vertices, and 0, 2 are not cut vertices. All of the vertices are cut vertices. So let us ask if 3 is the cut vertex. The answer is true, and if we ask for is 2 a cut vertex, it's false. Possibly that cut edge also will work. So 1, 2 is a cut edge. I think the bridge is the name that usually used, right? I don't know whether exactly the same name. I'm just trying. So most of the things, once you are familiar with the stage structure, if you try with some command, it may naturally work. One, two is a cut edge. And what about 1, 3? No. So we can loop and do all these things, and maybe we can remove cut edges, we can do several things like this. The documentation is really extensive. So now you can use the vertex cut, edge cut, etc. for getting the minimum edge cut, minimum vertex cut, etc. So so if you ask for vertex cut, what you will be getting is so suppose that if you ask for a vertex cut including one vertex and the other vertex, you will be getting that. So let us see a vertex cut. Vertex cut including one. Let us try. Vertex cut. What I will be getting? Vertex cut, minimum vertex cut. Okay, vertex cut between, oh, sorry, I need to specify vertex disconnecting. So what is the graph that I got? Let me just suppress this. So vertex cut disconnecting 1 and 3. So if you want to disconnect 1 and 3, let me just give 1, 3. Oh, they are adjacent vertices. Sorry. There must be a path between those two. So which one I should therefore use? Not edge, but path. So 6 and 2. Let me try. 6 and 2. So to disconnect 6 and 2, what is said here is disconnect 6 and 2. What is required? 1 needs to be disconnected, right? Therefore, to disconnect 6 and 2, the vertex cut required is just 1. That's what essentially it says. Now 2-3 more commands I will just try to explain, and after that I'm simply going to what do you call the Laplace transforms as well. Just 1 second. So one more thing probably I will tell. So suppose that we want to see all the graphs of size 3. Okay. Suppose that we want to see all the graphs of size 3. What we have size 3 in the sense that order 3 in fact. Order 3 in the sense that number of vertices equal to 3 exactly. Okay, 4. So for that, let's see, graphs 3. That's a command that we are supposed to use. What is this? So this is a graph generator. This will not give anything. For gene graphs 3, show G if I ask 4, I'll get all possible graphs with 3 vertices. All possible graphs of order 3. Now if I want to specify that number of edges, if I want to restrict, suppose that I want all graphs with exactly one edge. Here I have got the empty graph, not empty graph, what do you call vertex with a graph with all vertices, isolated vertex. I don't know if there is a name for that. Okay, let me just create one L, all graphs with size specified to be equal to 1. So G in L. So L is now the set of all graphs of order 3, size 1. Size 1. There is only 1. Because of maybe isomorphically. So maybe if you try with 4, and 2, we get more. Number 4, adjust 2. This is what it is. Now we can ask questions like is bipartite, etc. Now the diameter, which is the distance, the largest distance between vertices, I guess. So diameter also can be asked like this. Oh, sorry, we have not created a graph. I don't know on which graph it's now working. So we need to clearly define a graph. After that, we can ask. G is this, and diameter is 3, because 0 to 1, 1 to 3, 3 to 6. I think that's probably one of the diameters that it's taking. And distance also we can ask in the same way. Distance between two vertices, 0 and 3, say. Zero 3 distance is 2. Is that true? Yes. Now there exists more things like if is G connected, all such things we can ask. So as I told, the number of options, the number of commands available in graph theory in Sage. It's a very extensive set of commands and set of options are available for doing graph theory in SageMath. One full book actually can be devoted for understanding SageMath for graph theory. So I just explained some basic things. Now I will just I will probably this graph theory part I will probably stop, and little bit of Laplace transforms and little bit of Fourier series I wanted to finally explain, concluding the things, because previously these were the two topics I wanted to explain, and I want to explain one more thing, which is actually the group theory part and defining arbitrary operations, but unfortunately I could not find any such thing. But if you look at the group theory documentation in SageMath, what we can see is most of the usual groups are defined by default: permutation groups, dihedral group, Klein-4 group, all such things. What do you call direct product? All such things are actually defined there. So most of the practical purposes, already existing groups are more than enough. But for the arbitrary operations, I didn't actually see. I can see that the SageMath documentation on groups says that using multiplication, using sum, etc., we can define operations. But I could not find the proper example or explanation for that thing. I'm very sorry about that. I could not locate any such thing so far. So let me just a few things about Laplace transforms before concluding. So see that for Laplace transforms, essentially what we do is we take a function of variable t, and after that we convert it into variable s by doing some transformation. It's a transformation. Therefore, you are transforming one function from one form to other form. So the inverse transformation also exists. So the basic transformation part is very simple. So we need to define two variables as usual, s and t. X and y of course can be used, but traditionally the variables t and s are used for Laplace transforms. So defining. Now a function I am defining equal to a simple function. Take t itself. Just take f of Laplace with respect to t and s. That's it. Sorry, f is equal to, spelling mistake. Takes some time, probably it's loading the library. So what did I take? Maybe a show is a better option. 1 by s square. Try with t square, and even with, I don't know, even with n will it work? N is a symbolic variable, t to the power n. If I give, no, that symbolic thing is not accepted. I cannot derive formula here. T to any power is fine. T to the power 0, if I try with f equal to 1, that's not coming. So maybe I should try with t to the power 0. That's coming, because I think I need to give f as a function of t. Otherwise, I need to explicitly say that f is a function of t. If f is taken to be a constant, it's not accepted. I can probably give the instruction that interpret f to be a function instead of that. But I thought that this also is working equally, therefore it's fine. So the similar functions like cos x, sin x, sin t, this is not necessary. Sin t is this, sin t, t sin t is this, and exponential e to the power t is this. So most of the things are working like this. Now the inverse transform is also defined like this. So suppose that we ask for print. So we can just use the inverse after defining s and t like this. inverse. Okay, S to T. I need to define the variables as well. Let's retrieve. So maybe some other differential calculus related stuff also can be done using these things. I have not tried, but it seems that the derivative, the documentation, Laplace transform documentation is somewhat very good documentation is available in the SageMath library. So for most of the things, what you need to do is you need not have to go into any textbook or anything like that. For using SageMath, the only thing is that if you understand the basic things, more or less the once you have understood the philosophy of SageMath, that most of the mathematics related operations that we have in our mind mostly works without any issue. So you don't have to actually go into even the documentation. For many of these commands that we discussed today itself, I have been just trying randomly to see if the command I have in my mind, because of the experience that I probably have with SageMath system. So if I try that command, then most probably it works. So there is no such problem. Okay, so now one more thing before concluding, probably I will say, that is a Fourier series thing. Fourier series is actually really easy. The only thing is that we need to see how to define the coefficients. We have already done these things, but still remember that for finding the Fourier series thing, what we are supposed to do is we are supposed to find out all the Fourier coefficients. That's the only thing left in only difficulty in that Fourier series part. So for suppose that we want to find the Fourier series expansion for f of x equal to x square. Of course, this is not a periodic function. I think that's not necessary as well. So we need to compute the coefficients. So remember that a naught is nothing but in minus pi pi. So a naught is nothing but by the definition. Okay, let me copy and paste the things that I have already written somewhere. I'm copying and pasting certain things that I already have. This is from my website. I copied. Insert cell above. So mark down. So I already had tried these things. So I am just copying and pasting to save some time. So this is what we have. Fx is a piecewise defined polynomial function on minus L. Then the Fourier series expansion is this. So this is what we want. So a naught we want, by definition a naught is nothing but, so suppose that so we want essentially the coefficients a naught, a1, a2, etc., b naught, b1, b2, etc. See that Sage is a computer software, therefore you cannot expect an infinite series expansion, but on the other hand we can simply restrict our focus to certain number of terms. Okay, suppose that we try to find some 5 or 6 terms. So we need a list as well as b list, so that a naught, a1, etc., b1, b2, etc. So a is a list. Define a to be a list first of all, so that we can push every value of a naught, a1, etc. to this list. Defining a naught or appending to a naught. Which value? The a naught value I have to find. By definition, a naught is nothing but 1 by pi integral of f in the range minus pi to pi. 1 by pi integrate f in the range, f with respect to x in the range minus pi and cf afterwards, ca afterwards, sorry. We get this to be 2 by 3 into pi square. Now the same procedure, but now we have to do it in a loop, because we need the procedure for finding a1, a2, etc. are all the same. Or suppose that we want term count. Suppose we need terms to be equal to some 6 terms for remember that A0 is already found. So 1, 2, therefore you will be getting actually 5 terms. So we are going to do this thing in operation, in loop. So what we are going to find? We are going to find 1 by pi I integral f star cos nx in the range minus pi pi. That's what we are going to do, and that's that value we are going to push. A dot append 1 by pi star. See, we are going to integrate f in the range, f with respect to x in the range minus pi, and that's it. Now the A terms are all found. See this. Oh, is this correct? Oh, sorry. That cos is missing. F star cos nx. Sorry. That's a mistake. Where n is already varying. So these are the terms. So A values are already here. Now we do the same thing for the B values. But remember that here the B values are not really necessary because we already have this as an even function. X square is an even function, therefore that side part will be missing. Anyway, we will try. So let us create a B list as well. So B is here. But anyway, remember that B0 value is not actually necessary for us. So let us push a 0 value to this. We don't want B0, but anyway, since if we use this in the loop, otherwise the values will be having some index difference. So let us push 0 to that. We will not use that. B0 is not necessary for us. Let us keep it there. Otherwise, we may have to adjust this loop. So instead of cos nx, we have sin nx. Print A, print B. So see that this is an even function, therefore we are getting everything to be equal to 0. Okay, now we need to add. What do we need to add? So an, the half of a0, that's a formula. Half of a0 plus an cos pi x, cos n pi x by L, where L is the length of the, if minus L to L is the interval, then L is nothing but here pi. So the terms in the series, let us form. Series terms are, the first term is half of a0. Again creating an empty list. One by 2 a0, that's the first term. After that, let us do it in the loop. We are finding half a0 plus an cos nx, an cos n pi x by L plus bn sin n pi x by L. That's what we are trying to find. An cos pi n x by L. L here is pi plus Bn is not required here because it's 0. These are the terms. Now what do you want? Fourier series. This is sum of all these terms. Coming in the reverse order somehow. So it should have been read as my 1 by 3 pi square minus 4 cos x plus cos 2x minus 4 by 9 cos 3x plus 1 by 4 cos x, etc. So maybe to see if this actually matches with our expectations, we can try to plot if this graph is actually matching with f or not. F, that's one way to check if our computations are correct or not. Giving some color so that we can distinguish them. Red for the f function, blue for the, or the other way, green because it's the actual function, plotting. Green for the actual function, which is a parabola, and orange for the Fourier series function. See that there is of course a difference. Now suppose that if we reduce the number of terms to 3, say, how good is the approximation? So the approximation is, it's worse. If you increase the number of terms to 10, becoming better. 20 becomes lower, but much better. It's almost. So these many times. So this is how we can derive the Fourier series operation. But say that for finding out the Fourier series operation, you don't have to use any what you call extra modules or anything like that, because only basic integration is used here. But for Laplace transformation, since an infinite integral is involved there, it's better to make use of the already built-in function. Here there is no infinite operations used. So this is good enough.
Sir, here can we do the integration by treating n as a variable? Later on we will vary the 10.
I have not tried that. So what you want is just integrate without giving any value for n. So non-numeric thing, right?
Right. N is a variable.
But the problem here is that you cannot append an in that case, because an has to be always a value.
Right. A is the value.
Yeah, A is a list.
And cos,
A is a list.
Cos and
In that case, you need
and
to.
if at n, because n is a variable.
So what you are asking is, if you give f cos nx, okay, let us just try. What is the harm in trying? Part of that only we will see. The first part we will see. Let us delete this. So here you want to, of course the integration most probably will happen, but I don't know whether the other things. So if you ask for here we are doing in a loop, right? So let us, instead of that, this is what you wanted essentially, right?
This is not visible.
I have not. Okay, sorry. Let me just copy this part. Only this part I will copy. So define n to be variable, removing this as well. This is what you want to call as an, right?
Yes, sir.
Yes, it's working. It can integrate. So it gives something like this, but I don't know whether it's that friendly or not.
NPy, sin NPy should be 0.
Yeah, because that's that is not it is not evaluating that because it doesn't know what this n is.
Treating as an integer.
N is n cannot be treated as an integer because Sage thinks that it's just a symbolic thing. It can be even rational.
Now we'll take the sum up to n terms.
Yes, yes. Then now whatever you want, you can do. You can in fact take a to be you can define a to be a function of n, right? Define a to be a function of n, and a of n is this.
Okay.
Now add it in a loop.
Thank you, sir.
So most of the symbolic things are possible that you can actually do, and exactly the same result you will be getting, but the only thing here is that you will be getting a formula like kind of thing instead of numerical thing. So the previous one we were getting the complete numerical evaluation, but here you are getting, here you are getting a symbolic evaluation. That's it. Okay, so probably with this I will stop because I think I could probably discuss the things that were planned for today, and if there are any questions related to these things, I can try to answer. As I told in the graph theory thing, the scope of Sage Mathematics is very extensive. You can find the documentation page of SageMath itself is really huge. Creating Hamiltonian, complete, Peterson, cubic graph, all such things are already available there. Most of the working graph theory can be, including even up to the research level thing, can be probably carried out in SageMath is what I think. So I do not have much expertise in graph theory because I am not a person working in that research area. Probably if you are doing some serious working graph theory, maybe you can better understand what exactly these options are and where these are used. I can just give an introduction to that thing because I know only that much in graph theory. So I will probably stop. If there are any questions, I can try to answer. Thank you very much.
Is there any question, please?
Yeah. Excuse me, sir.
Yes, please.
Here we have find the Laplace transformation. Can it be possible that the finding Laplace transformation is expand or expressed in partial fraction?
I didn't understand. Express Laplace transformation in?
We have find the Laplace transformation of the given function, and can given function is expand in the partial fraction.
See, we have already seen that we can split it in the partial fraction form. We have already seen one command while trying to integrate. The partial fraction itself is a command there. If that's what you are asking for, you are actually getting a function in terms of s, right? When you are applying the transformation, you are getting a function in terms of s. If you are asking that whether we can split it into partial fraction, the answer is yes, because already there is a command called partial fraction itself in SageMath.
There is not necessary to give any other command right the partial fraction. They are automatically separated.
Where?
I am just asking, there is no need to write a partial fraction word in SageMath.
No. Sage is automatically doing that. Then why do we need that? No, the only thing is that sometimes it can really happen that if you are not splitting certain things into partial fractions, Sage may give a very complex expression which you may have to simplify. For that, you may use the function full simplify. I think previously we have seen that. One full simplify function was there, and simplify itself was there. Sometimes you may have to use. See, what we have to understand is that this is created by some programmer, some mathematician. They might have probably thought that okay, getting the final result is more than enough. But if you want some simpler result, maybe you may have to use this full simplify. Then you may have to split into partial fraction for getting better results. And if you apply the partial fraction and then if you apply Laplace transformation, you may get a differently looking result out also. That's also possible. But they are going to be all the same, but it may look differently. You can of course do that.
Yes. Thank you, sir.
Thank you.
So if there is no question, then we conclude for this section, and we have came to the conclusion section of our workshop. And I request some of the participants to share your feedback in few words, please. I request Professor Venas to share your views.
Yes, hello. I'm Dr. Veena Singh from MLT PG College, Balrampur. I'm very grateful to the coordinator, Dr. Prasad sir, for organizing this workshop on SageMath, and it is very useful for us. And actually, we have conducted this in the evening, so it was possible for us to attend this workshop, and it was conducted in online mode, so it is possible for us to attend this. And I'm also grateful to all the members of the organizing committee who have provided this platform.
Thank you.
And I'm very thankful to resource person, Dr. Vishnu sir, for giving such nice lectures and for providing this. You have solved every problem. We have even you have not prepared, but you have given your best, and I'm very thankful to the resource person, and it was very interactive. You have always encouraged us to interact with you, and
Thank you very much.
I'm very thankful, Dr. Vishnu sir, for giving this Google document, provided us this Google document. Thank you very much.
Professor Krishna. Please come forward and share your feedback, please. Anyone. Dr. Manoj Sharma is there. If anyone interested to give a feedback right now, please. Or otherwise you can type in the chat box. That's also okay, fine.
Please provide the email ID of resource person, so that if we have any problem, then we can ask.
I'm just typing. I'm just typing now. 1 second. Yeah, it's here. It's already in the chat box.
So Anil sir, shall we conclude? Anil sir?
Yes, please conclude. Please conclude.
Oh. So we have came into the conclusion section of our workshop. It is my pleasure to extend all of thanks. dear colleagues, first and foremost, on behalf of our Department of Mathematics, University of Calicut, I extend my thanks to Professor Vishnu Nandudiri for his fruitful sections enriched with into about SageMath. And we are very grateful to Professor Vishnu for timely completion of the workshop in spite of his personal loss during this fellowship. Thank you very much, sir. No words to thank our beloved head of the department, Professor Anil Kumar, who made this workshop possible right from the stage of proposal till certificate issue. Thank you very much, sir. I thank one and all the participants of this workshop. Thank you again. And your certificates will issue through online shortly. And if you have any doubts or any spelling errors or any errors in your designation, please share. Then we will make another and share with you. Okay. If you have any doubts regarding this, please share your thoughts. And if you have any doubts on this SageMath or Python, our resource person is always ready to help all of us. And once again, I thank you, especially Professor Vishnu Nandudiri and all your participants. Thank you very much.
Thank you all. Thank you.